what about multiple comparisons that I mentioned? Well, this idea that we have a significant ANOVA, but all that does is tell us that there are some group differences somewhere, but we don't know where. So in order to find those, we have to use some further investigation. There's more things we have to do. And this is where I mentioned early on, it sounds a bit contradictory. Where we're saying, hey, you can't do multiple t-tests because it inflates error and it causes problems, it's inefficient and precise. So let's do this ANOVA instead. But then when we're done with the ANOVA, we're like, well, now we got to do some t-tests. So it's sort of true, but we're going to do t-tests and compare the individual groups in a way that sort of helps to keep the type 1 error down, right? And the ANOVA actually acts as sort of a gateway. So if your ANOVA is significant, you then proceed to follow that ANOVA with some comparisons, doing multiple comparisons across the groups. However, if your ANOVA is not significant, you stop. There's no point in doing additional comparisons across the groups and things if the ANOVA says there are no differences. So the ANOVA acts as sort of a gateway, sort of a switch, right? So if the ANOVA is significant, all right, now let's look for some more, some difference between groups. However, if the ANOVA is not significant, you stop. Okay. So let's talk about, in this case, our ANOVA was significant. So how do we go forward with that? What do we do? So a significant F only shows that not all groups are equal. So we want to know what groups are different. We actually want to know where the differences are, because again, if I'm a market researcher and trying to do this study on baby food brands, I don't want to know that they're different. I want to know which one's the best, which one's the worst. I actually want to know exactly what's going on. And these procedures that we're going to use are designed to control what they call the family-wise error rate. So it's just a fancy way of saying that if I'm doing multiple t-tests or multiple kinds of comparisons, I want to keep the overall alpha level at 0.05, right? So I want 0.05 across multiple tests instead of being 0.5 at each test, because if I do 0.5 at each test, I know I'm going to be inflating my alpha and having more type 1 errors. So I'm going to try to control this family-wise error rate, and I'm going to contrast that with what a per comparison error rate would look like and why it gets more inflated that way. So most of these approaches, we're going to talk about this Tukey test and another one called the Bonferroni adjustment. Most of these work by trying to reduce the significance level of each test. I mean, a real simple idea is if I'm doing 5 t-tests and I want the overall alpha level to be 0.05, well, then I'll do each of those t-tests at 0.01, so that collectively they add up to 0.05, right? So the more tests you run, the more likely you are to make a type 1 error. So if we actually do the alpha level at a lower level for each test, collectively it'll add up to sort of 0.05 or something like that. We're able to sort of control for it by doing that. So it's also a good reason to hold down the number of tests, meaning that even though, like with 10 groups, you can do 45 t-tests, it doesn't actually mean you need to do 45 t-tests. Maybe you only need to do 5 of those. You know, it's a good reason to sort of to minimize the amount of actual tests that you're going to be performing, so you don't have to control for it so much. Right? Because each t-test you do requires another alpha level, you know, another 5% alpha or whatever. So if you're trying to keep the overall family-wise error rate down, you can do as few tests as you can, or as few tests as makes sense, and then make sure that they all collectively add up to 0.05, and that'll be a way of sort of controlling for inflating type 1 error and having too many problems, okay? There's lots of these, okay? So I'm only talking about a couple of them. I'm going to tell you 3. So 3 of them. There are lots of them. If you go, especially if you're in SPSS working on labs and stuff, and you're doing the ANOVA and you look at post-hoc tests, you can see the laundry list of them. There's Dunitz and Chaffee and a whole bunch. So we're only talking about 3. I'm going to talk about the Tukey honestly significant difference test, the Fisher's least square difference test, and the Bonferroni, which is really not a test in and of itself. It's just a way of sort of addressing the critical values in doing each of the tests. Okay, so what the Tukey test is, it's the honestly significant difference controls for all possible pairwise comparisons. So this is it assumes that you're going to do every conceivable pair. So if you have 10 groups, this Tukey honestly significant difference test is going to assume that you're going to do all 45 pairwise comparisons between the groups. And what it does is it actually creates a critical difference, which is sort of like a critical value. Okay, it creates a critical difference, and then all you have to do is subtract the means between your groups, compare it to that critical difference. If your mean difference is larger than the critical difference, then those groups are significantly different. If your mean difference is not larger than the critical difference, then those two groups are not significantly different. So it makes it a little easier, sort of creates a critical mean difference that you need, like the minimum mean difference. And any mean difference larger than that then would show a significant difference between those groups. So it becomes a little easier to sort of figure out once you get that critical difference. All right, so here we have the critical difference, right, which is going to equal to this Q value. And Q value comes from a table, the studentized range statistic table, which is oftentimes just referred to as a Q table. The MS within groups is just going to come straight out of the ANOVA. And this NA is, this refers to it's just the n assuming that the n's are equal. Right? I forgot, it's like called the harmonic n, or this is the harmonic n. It's just that it's assuming that you have equal n here, and you can divide by that n. If you have unequal n, then you can actually compute it this way. So same Q, same MS within groups. It's just now you're taking 1 over Ni, which is one of the groups, plus 1 over Nj, which is the other group, adding them together, taking the whole thing and dividing it by 2. Just so you can do it for groups that have unequal n as well. For our example, we have equal n's, so we're going to end up sticking with this version up here, which is a little bit easier anyway. But it's possible to do with unequal n using this sort of version, where I think this part in the middle here is called the harmonic n, or something like that, that they use for these tests. So let's compare Beechnut to Gerber. All right, so to compute the critical difference value, and so let me back up. Why did I pick Beechnut and Gerber? Let me go forward a second. Beechnut is 4.6, Gerber is 8.4. If there's going to be a difference someplace, it's likely going to occur between the mean that is the largest and the mean that's the smallest, right? So if I find a significant ANOVA, the first place I'm going to likely look is to figure out the biggest difference, 4.6 versus 8.4. If that isn't significant with the Tukey test, none of the others are going to be significant either, because they're all smaller. So I can start there. To compute the critical difference value, we need to first find the value for Q. Q depends on alpha, the total number of groups, and the degrees of freedom for error. So we have 3 groups, alpha is 0.5, degrees of freedom for error is 12. So let's look at the Q table and see what we find. Look at that, studentized range statistic Q table. So it says here on the top, total number of groups. This is not the between groups degrees of freedom, but the total number of groups. So I have 3 total groups. So I'm going to start on this column here. And then I have 12 degrees of freedom for error. And then there's 2 choices, 0.05 alpha and 0.01 alpha. So I want 12 degrees of freedom for my error term. I want 3 groups. So that's why it's this 3.77 number is my Q value I'm going to use. I need a couple things. So I have this 3.77 number that gets plugged in here. 3.77. Up at the top, I need my mean square within groups. So where do I find that? Well, that was in my table. I think we erased. But let's go back and see if I can't find something. So within groups is 34.4 divided by 12. 34.4 divided by 12 is going to be our within groups variance. 34.4 divided by 12 is 2.867. Alright, so that means 2.867 is our mean square within groups. I have, I'm dealing with 5 babies in each group, so that's our sort of, our n value there. So I'm going to take 2.867 divided by 5 is 2.867 divided by 5 equals 0.5734. I'm going to take the square root of that. I get 0.757. So I'm going to take 0.757 times 3.77 equals, so this is 2.86. It's really 2.85476, whatever. So like the 6 makes a 7 and 8, 8 makes a 4 or 5, 5 makes a 5 and 6. So it's really like something, if you really want to get more specific, it's 2.855 or something like that. 2.855, if you want to go to 3 decimals. Just to differentiate between, because it looks, you know, remarkably similar to our original value for our MS within groups. It's not the same number. So 2.855. Okay, so it's not, these two numbers aren't the same, they're just similar. Okay, so this gives us the minimum mean difference we need. So any two groups that have a mean difference that's larger than 2.855 is then significant, given this honestly significant difference. So the difference between Gerber, 8.4, and Beechnut, which is 4.6, is 3.8. Since 3.8 is larger than our 2.855 value, then the difference is significant using a critical difference, using this Tukey critical difference. So what does this mean exactly? So this is only just one of them. So I could do the others. What about if I do 6 minus 4.6? All right, that's 1.4. 6 minus 4.6 equals 1.4. So this equals 1.4. Well, 1.4 is less than 2.86. So this one, so this is now, this is Del Monte versus Beechnut. This is not significant. So what about the other one? 8.4 minus 6. So that's going to be Gerber minus Del Monte. So 8.4 minus 6 equals 8.4 minus 6 equals 2.4. All right, so 2.4 is also not bigger than 2.86. So this one's also not significant with the critical difference. So knowing that, and knowing it with this critical difference, what I can conclude from that is the ANOVA told me that not all groups were equal. Okay, great. So I did this follow-up test that controlled for the alpha level, because I'm doing 3 different tests, 3 different comparisons. And it gave me this critical difference of 2.86. And it told me that Gerber is significantly different than Beechnut, but that's it. So what I can conclude, as a market researcher, I know that babies prefer Gerber over Beechnut, but that's really the only thing I might be able to conclude. I don't know that they prefer Gerber significantly over Del Monte, or Del Monte significantly over Beechnut. The only thing I can conclude is that the babies did not prefer the baby foods the same. They're not equal, but the main difference seems to be that babies prefer Gerber over Del Monte, and any other differences are sort of inconclusive. The Tukey test that we just covered assumes that you're going to be doing every possible pair of comparisons you can do between groups that you have in your independent variable. And this, of course, is following an ANOVA, and it's considered a post hoc test. The test is done sort of after the fact. So the Tukey test, because it assumes you're doing all of those comparisons, it keeps the overall alpha level at 0.05 by making each of the comparisons you're doing, it makes them have a stricter, more conservative alpha level, so that when it combined together, you get an overall alpha level of 0.05. So there's a couple things about that. So you have to have an overall significant ANOVA, and then you're assuming you're doing all these tests. So let's further control the alpha level for each test so that we're not inflating type 1, type 1 errors, not inflating alpha. So Fisher's here, the Fisher's LSD procedure, takes a slightly more sort of liberal approach to that. So we get a significant overall ANOVA, which tells us there's group difference somewhere, and that ANOVA controls for the overall alpha level. So the Fisher's procedure here is saying, well, since the overall ANOVA is significant and it already controls for the sort of family-wise or the overall alpha level, we don't need to do more of that. We can actually take each of the follow-up t-tests a little bit more liberally, do them at a regular 0.05 alpha level for each one, because the ANOVA has already done that control for us. So it still requires, an overall significant F, right? So your ANOVA has to be significant. But we're going to run what is essentially standard t-tests, or we're just going to do a regular t-test with one alteration. Now, if you remember back when we did independent samples t-tests, we had to pool together the variances of the two groups we were comparing to create a pooled variance. And then we used that pooled variance to then estimate sigma, or sigma squared, from our population, and we were able to plug that pooled estimate, the pooled variance estimate, in for our standard error, and it's supposed to give us a more sort of accurate depiction of what the standard error would be like had we been able to get the population value. So with the independent samples t-test, we had two independent groups, and the logic was, well, each of those groups is estimating the population. So if this is our population, we have a population variance, and we have some variance from one group and a variance from another group. Each of those, right, is estimating the population. So since each of those is a good estimate of the population, we can simply sort of average the two of them. And that average, that pool, right, we're going to pool them, is going to be a better estimate of the population than either of them alone. Right? That was the logic. We have two estimates. Let's use those two estimates to create a better estimate of our population. We also said, well, we should probably take the ends of each one into account, because if one of them has a larger sample size, it's probably a better estimate and should contribute to the estimate of the population more. So that's when we got that n1 minus 1 times the variance of 1 plus n2 minus 1 times the variance of 2 over the common standard degrees of freedom. Right, so we got this whole thing. We call this S squared pooled. Okay. That was our pooled variance. Awesome. We had two groups. We did that. It made sense. At least I hope it does. Okay. Well, in our example, we have three groups, and you may have 4 or 5 or 10 or 20 groups. I mean, I don't really recommend doing that many groups, but we're going to have more than 2, and we know that we already said that our variance within groups equals to essentially a pooled variance. It's just a pooled variance with more groups. So if that's true, this is just a pooled variance with more groups, then we can just replace the S squared pooled we have from our independent samples test with this mean square within groups, and use this mean square within groups, remember that's what this is, mean square within groups equals the variance within groups equals pooled variance. It's just, like in our example, we have 3 groups instead of 2. So this is really just a pooled error term, but with more degrees of freedom, because it's pooled across more treatment groups. So instead of doing our independent samples test, these t-tests we're gonna do sort of following our ANOVA, instead of doing them by estimating a different pooled variance for every pair that we have, let's just use the one measure of pooled variance we've already calculated for the ANOVA and replace that in for the pooled variance and do the t-test from there. So since we've talked about the independent samples t-test before, these steps are the same. They're pretty much, they're the same steps, pretty straightforward, with one slight tweak that actually in a way makes it easier. We've already done the work to find this MS within groups, right? Which is really just an extended pooled variance estimate. So we're just going to use that instead of trying to find one for every pair that we want to compare. Because imagine if we're doing, let's say we had 5 groups, I want to compare group 1 and group 2, I'd have to do a pooled variance for those 2. And I have group 1 versus group 3, I'm going to need a different pooled variance, group 1 versus group 4, a different one. Every pair I'm going to re-estimate the pooled variance. That seems silly. I have 5 groups, why not just use all 5 of them to generate one overall pooled variance, which is what this does. Now in our example we have 3 groups, not 5, but the idea is the same. Let's use the pooled variance that includes all 3 of the groups instead of doing it for each pair. We plug that in for our pooled variance and use that as our estimate of the population variance, which is more accurate. It's going to be a closer estimate anyway because we're using more groups, more information. So let's say we want to compare beechnut to Gerber. I need a standard error for the difference between the 2 means for beechnut and Gerber. So I'm going to take my mean square within groups that we found from our ANOVA table. And I'm going to plug that in to this equation, dividing by the n for beechnut and dividing by the n for Gerber. Now it just happens in our example these n's are the same, which is why you see 5 and 5 here. And you see the same 2.867, which is our mean square within groups, again twice. But these numbers could be different, and you're able to account for that. So if we plug those in, add them together, take the square root, we get that our standard error of the difference between the 2 means is 1.071. So now all we need to do is subtract the means, 8.4 minus 4.6, and divide by that standard error, and I get a 3.55 is my t value. So this is my sort of Fisher's t. So you may have been looking up there and thinking, right, well, why is it called LSD? Well, that LSD does not stand for what you think it stands for. It stands for Fisher's least square difference. Okay, so, or least significant difference or something like that. It does not stand for lysergic acid diethylamide, which is what the drug name comes from, which I always thought was odd because it's LSD, yet the words are LAD. I don't really know why that is, but it always caught my attention the first time. I'm like, LSD. In this procedure, we're really just looking for, I think it's the least significant difference. We're just looking for what is, the significant differences between these groups using this substitution method. And then all we gotta do is look up. Now we can look up the T critical with, we have 2 groups in this case, both with 5. So 5 plus 5 minus 2 equals 8. We looked it up. You can do it either one-tailed or two-tailed, depending on what you hypothesize. But I think often it's done two-tailed, just because we're comparing multiple groups, and that sort of matches up with the ANOVA procedure. Anyway, so you find a critical value in the table, and you compare your Fisher's version of T, to that critical value, and you figure out if the 2 groups are significantly different. Right? And you can do this for any of the pairs. And since they all have five babies in all the groups, this standard error will be the same regardless of which 2 groups you're choosing. So you can subtract the means, divide by this, and get a t for any of the pairs of groups, and you can compare them using this LSD procedure. The main thing here is that Fisher's, in contrast to Tukey, does not do any adjustments, per test. They're doing each one of those at a 0.05 level. So technically, you're doing 3 tests at 0.05. So you're giving yourself, something more like 15% chance of making a type 1 error. But the logic behind that is, and what Fisher sort of argued, is that, well, look, the ANOVA already took care of the let's control for all the groups, and so we don't have to do that anymore. So it's a little bit more liberal of an approach to doing sort of post hoc comparisons, multi-comparisons, after a significant ANOVA. Right, that's the main takeaway. Tukey does the adjustments and assumes you're doing all pairs, so it controls for every conceivable pair you might do. And Fisher's does not control for anything after the fact, and it relies on the ANOVA to have done that control in the first place. So the last one I'm going to mention here is not really a different procedure, but it's a different way of thinking about how to maintain an overall alpha level 0.05 for your post hoc tests. By the way, I keep saying post hoc, and I probably should mention that too, that there's 2 things that are in sort of contrast. So one is this term a priori, right? The other one is post hoc. So a priori means sort of prior to, right? So if you have hypotheses about group differences and things before you collect data, this is considered an a priori hypothesis. So you can actually test those directly without really any consequence, without any adjustments or any issues. The trouble comes down when you're doing the test post hoc. So when you do an ANOVA, and you're saying, look, I want to know if there's differences anywhere between these groups. And then after the fact, you look at, well, okay, Gerber seems to have a higher mean than Beechnut, so let's look to see if that's a significant difference, right? So you're now allowing the data to tell you where to look, what groups to compare. So you're doing it after the fact. You're doing it post hoc. So whenever you do anything post hoc is usually going to come with some kind of adjustment. Right? So going to come with some kind of post hoc adjustment to the test to adjust for the fact that you're letting the data tell you where to look, what groups to compare, or that you're just doing every comparison possible. So when you think about Tukey, it falls under this category, the Tukey test, right? So it's a post hoc test. It's saying, look, you're doing these tests after the ANOVA. We're gonna take that adjustment and make sure that we're not inflating alpha. Where the LSD procedure, even though it's done after the fact, it's not taking the post hoc adjustment. So yes, it's a post hoc test in the sense of it coming afterwards, but it's not post hoc in terms of, we don't treat it that way. We treat them as if they're planned or a sort of a priori comparisons, and we don't adjust anything because, as Fisher, argued, the ANOVA already did that adjustment. The Bonferroni t-test is another sort of example of a post hoc approach. Whether you're doing the Fisher's version of t-tests or just doing regular t-tests, it's basically saying, look, we don't have to change anything about the test itself, right? The test can stay the same. We can do a regular t-test. We don't have to do, substitute in the mean square for within groups. We can do it however we want. We can just use regular pool variance. We can do whatever version you want to do to compare them. Okay, not Tukey, but like regular t-test or an LSD procedure. Why don't we just adjust the critical value? Right? So if we're looking at a critical value, typically we look it up for 0.05. If we want the overall alpha level to remain at 0.05, well, why not just do each individual t-test at a smaller alpha level so that they add up? You can combine them to an alpha of 0.05. All right, so run t-tests between pairs or groups as usual. Again, you can do it as a regular t-test, or you can do them as a Fisher's version. You want to hold down the number of tests. So only test those groups or make those comparisons that you need to, or that you want to, or that you have some hypotheses about. And then you're going to reject if your t value exceeds critical value in a bond-forming table. Now, either in a, so there is a bond-forming table, but I don't think I even provided it to you. So there's a bond-forming table that gives you adjusted critical values, or you can just take your alpha and sort of divide it by the number of tests and do each of, look up critical values for that smaller alpha level and do each of your t-tests or compare each of your t-tests to that critical value at that smaller alpha. Right, this works by using a stricter value for alpha for each comparison, right? So there's either a table, bond-forming table that already adjusted for you, or you can do, take alpha divided by the number of t-tests. There's a problem here, like with our tables, we don't have a lot of crazy in-between alpha levels. Basically, I think it goes like 0.1, 0.05, 0.01, 0.001 or something. There's not a whole lot of in-between. So you may have to, divide by the number of tests and then maybe go even a little stricter, which I'll show you with our example. Now, you may have to sort of go a little bit beyond what you need to keep it at 0.05 because we may not have that alpha level available in a table. So let's say, the typical alpha level is 0.05. That's what we typically do. So critical value for each alpha, or of the alpha for each test is set at the 0.05 we typically use, divided by C, where C is the number of tests you want to run. So in our example, we have 3 groups, and therefore we can do 3 t-tests. So if we assume I want to keep the family-wise, the overall alpha level 0.05, with 3 tests, each test must be significant at a 0.05 divided by 3 or at a 0.0167 level. So if each individual t-test, again, whether a regular straightforward t-test or the Fisher's LSD version, is significant at this level, then I know that the overall alpha level is at 0.05, and it sort of keeps everything sort of from overinflating the type 1 errors. So if you're doing this through like SPSS or R or SAS or any program, you can just look at the printout for each t-test and see if the significance level is smaller than this. So if you get a 0.005 or a 0.015 or something, they're less, it's less than this level, then that t-test is significant with a bond-forming correction. By hand, it's a little bit trickier because if you're looking up in our table, we don't have 0.0167. I think we have 0.025 and 0.01. So we'd have to likely use 0.01, which is stricter than what we want, and do each test at a 0.01, which means our family-wise error rate is not going to be 0.05, it's going to be 0.03, which is again stricter, but it will keep us from overinflating if we use that anyway. So just going to a stricter level because we don't have that. We don't have a column for every conceivable alpha level in our T table. But that's it. I mean, there's nothing more to this. It's not a different approach to a test. It doesn't do anything except for, all right, let's change the alpha level. Let's change the critical value that we're going to use for each test by using a smaller test for each individual t-test so that over all the t-tests we're going to do, they add up to 0.05. And that's it. It's a pretty straightforward idea, but it does allow us to get an adjusted version of a t-test without changing much except for looking at a different critical value. Okay. So one of the things that every test that you do, every test that you're going to do in statistics is going to have some kind of assumption. There's like a line here. Usually a set of assumptions. We talked a little bit about this we talked about independent samples t-test. With an independent samples t-test, we assumed that we could pool together the variances because we were assuming that they were homogeneous, right? This idea that we could pool the variances of the two groups together because they're either coming from the same population, therefore estimating the same population variance, or because we need the two groups from two different populations to be similar enough to be able to be compared. So that assumption, the homogeneity of variance assumption, is something we assume when we're doing a t-test. We also assume that if we had enough people in each sample, that our sampling distribution of the means would be normally distributed. Right? So we're assuming normality, we're assuming homogeneity variance. All these things are sort of assumptions that if you don't meet that assumption, if there's some reason to believe that it doesn't quite meet your data, then it makes you question the validity or the legitimacy of the test that you're doing. So you get a significant test, but now you're like, well, I don't know if I should trust it because I didn't meet the things that I thought I should assume. The variances are dramatically different. I have a small n, and therefore I can't assume homogeneity I can't assume normality of the sampling distribution. If those things are true, then it brings your results into question. It makes you wonder, am I really getting the correct result, right? So seeing as how ANOVA is an extension of the independent samples t-test, this between groups ANOVA that we're doing is an extension, the assumptions remain essentially the same. Right? We're going to assume that our observations are normally distributed within each population. Okay, so even though it says observations normally distributed, the real thing comes down to we're going to assume that we have either enough people or that our population is normally distributed, so that we can so that we know that the sampling distribution of means would be normally distributed as well. Right, so that's where this first one is coming from. We're assuming that we get a normal distribution of means from our samples based on the sample size or based on the fact the population is large. Sorry, based on the fact the population is normally distributed. We're assuming the population variances are equal. Right, so this is again the homogeneity of variance assumption, or another word for that, another term for that is this word homoscedasticity. That's really a word, homoscedasticity, which is just a single word, and this comes out of sort of more a regression approach, but it means the same idea, that the variances are roughly equal across groups. And for this to be a between groups, just like with independent samples t-test, we're assuming that observations are independent, that people in the different groups are not related, and we don't have triplets of babies that we're assigning one triplet to each group to eat different food. These are different babies that were randomly assigned. They're not related. There's no dependencies between them. So just like the independent samples t-test, this sort of between groups ANOVA is like an extension. It's basically an independent samples analysis of variance. Right? They're definitely the between groups ANOVA is definitely an extension of the independent samples t-test. So we basically have the same assumptions. Now there's been a lot of study on the analysis of variance, and a term that gets used a lot to describe an ANOVA, the analysis of variance, is this word robust. So a robust test is one that is not greatly affected by violations of assumptions. So analysis of variance is generally robust to the first two assumptions. So let's go back. It's robust to observations are normally distributed and population variances are equal. So what that means is you could have some evidence that your population is not normal, or you have small n. You can have some evidence that your variances are very different from one another, that you're violating this assumption. And the ANOVA typically still works pretty well. It actually is a fairly trustworthy, unbiased sort of approach to comparing groups. That's what robust means, right? So that it actually works well despite violating these assumptions. The last one, though, is sort of a requirement. So if you're doing a between groups ANOVA, the groups do have to be independent. And if they're not, if there are dependencies in it, then that's a problem. You shouldn't be doing a between groups ANOVA, you should be doing something else, like a repeated measures ANOVA, which we'll talk about shortly, to address the fact that they're not independent. And we can actually do that. And that's basically an extension of the dependent samples t-test. So if you're going to do a between groups ANOVA, you need to make sure that the observations are independent. You should try to make sure that these assumptions are met, but if they're not, it's not the end of the world. And just as a reminder, the way that we tested for this is the same in the independent sample t-test, is the same here. We can use this F-max test, which is you're going to take whichever group has the largest variance, right, over the group with the smallest variance. I don't know why I'm writing it so small over here. As long as that is less than or equal to 10, it's considered homogeneous. Okay, so that's the same thing we talked about before. It still applies here. So if you want to test to see if you have homogeneous variances, this is an easy way to do it by hand. In SPSS, it uses you get a test called Levene's test, and Levene's test is doing the same thing. It's testing for homogeneity variance. It's just this is very, very conservative. So this is a very strict test, and you will reject the homogeneity variance assumption more often than you probably should. So anytime you get a significant Levene's test, which is bad, you probably want to follow it up with an F-max test to check it. All right, so let's talk, the last part of this is talk about effect size with ANOVA. So we talked about effect size as the sort of Cohen's d or Cohen's d hat measure that is often used in one sample, dependent sample, and independent samples t-tests. And you can actually still use that. You still see people using Cohen's d with ANOVAs, but it gets a little tricky in terms of, well, how do you calculate it? Because Cohen's d is the difference between two groups over some standard deviation. So we have the pooled variance. We can probably take the square root of that and get a standard deviation. That's fine. But if I want to get an effect size, like an overall effect size for the multiple groups that I have, which groups do I use? Do I use the groups that are the farthest apart, like the biggest mean and the smallest mean? That'll give me the largest effect. Do I use the groups that have the smallest difference? Do I do an effect size for every single pair I can and sort of average them? It's sort of not real clear on how to apply sort of Cohen's d successfully. So we're going to think about a different way of thinking about effect size for group differences when we have multiple groups beyond just the two. Okay. So I'm going to give you two different versions. One of them is called eta squared. That's the Greek letter eta there. Eta squared, which is super easy to calculate. It's easy to interpret. People like it that way because it actually has a very easy interpretation. It's somewhat biased on the high side. So what does that mean? That whenever we apply this equation to an ANOVA, we tend to overestimate the effect size. We know that there tends to be a bias on it being a bit too big compared to the population value. Right? But we can actually interpret it pretty easily. It's percent of variation in the data that can be attributed to treatment differences. So another way of saying that is of the total sort of variability, the total deviations that we have, sum of square deviations, we add them all those up, we get a total sum of squares for all of those deviations around the mean. All right, well, how much of that total is due to variations between the groups? So this gives us a percentage. The larger the percentage, the larger the group differences are, the more variability there are between groups. Okay, so this is a way of looking at, relative to the total variability, how much of an effect is the different groups, in this case the different treatments, the different brands of baby food, how much is that impacting the respondents' individual scores around the grand mean? So the bigger this is, the larger the effect is. All right, more between group variance relative to total means a larger effect, a larger difference between those groups. All right. The problem is, again, it's overestimated. And this is one of those cases where we break the rule a little bit. So the rule generally is if we're talking about a sample, we use Latin letters, right? So like D, Cohen's D. We use, if we're talking, for samples like S for standard deviation, M for mean, okay? And then we usually use Greek letters to refer to population values, things that are going on in the population. So this is one of those times we break this because eta squared is a sample statistic, right? It tells you what's going on in the sample, and we know that it tends to be overestimated relative to the population. So this really is a sample value, and so the fact we use a Greek letter here sort of breaks our typical rules about Greek and Latin letters assigned to things. So we have this other one, it's a different approach a little bit, called omega squared, where it's less biased than eta squared. It's not as intuitive, it's not as easy to calculate, but what it does do is give you a better estimate of the population. And even here, since we're using sample values and we're estimating population, this is really, you might see this, some places, is really omega hat squared. It's a population estimate. Okay, so it's less biased because it tries to address some of the issues of overestimation that eta squared has. So we adjust both the numerator and the denominator with mean square within groups. All right, since we know, like with an f-test, that the numerator on an f-test has both real differences, real variation, plus random variation. It has some random variation in it as well. So why don't we just subtract that out? Why don't we get rid of the random part in the top? So what this does is sum of squares between groups. I subtract out this is my number of groups, for every group except for one of them, for our degrees of freedom, because every single group tends to contribute some random error to the system. So why don't we just subtract that out? We'll take our k minus 1 times that. I'm going to subtract it out of the sum of squares between groups to get rid of at least as much error as we can out of the top. And then, for whatever reason, and I don't remember why it is exactly, we're going to add one mean square error back to the bottom. So we're going to take sum of squares total plus 1 of our mean square errors down here. And we're going to so divide these out. What we're going to get is an adjusted score for our effect size, which is going to be smaller than eta squared, but it should be closer, or at least a better estimate of the population value, which is why we're making all these adjustments. So let's plug some of these numbers in. Going back to our ANOVA table, we had that our sum of squares between groups was 36.933. Our sum of squares total was 71.333. We divide those out, you get 0.518. And you can see, the eta squared is 0.518, which means roughly 52% of the variability in spoonfuls of peas, right, can be accounted for by brand of food. So that means of all the things that can affect babies eating peas, okay, there's lots of things that could be impacting their willingness to eat strained peas. It seems like at least 52%, more than half of that variability, is due to which brand they were being fed. That seems quite a lot. That's a pretty large effect. If we do it as an omega squared, and we actually correct for the error and try to make it a closer estimate of the population, and we plug all the numbers in, so our sum of squares between groups, our mean square for within groups was 2.867. All right, so we're just plugging those numbers in. We subtract and divide all that out. Excuse me. We get 0.421, which is a much smaller estimate, 42%. So this is supposed to be a less biased estimate, closer to the population. Note that it is smaller. Typically, omega squared is going to be a smaller estimate than eta squared, because it's eta squared is considered sort of overestimated. Oftentimes, it is. It tends to be on the high side when estimating the effect size. Okay, so but still, it's still a large amount. 42% of the variability, the differences between babies eating food, okay, period, eating these strained peas. 42% of that variability is due to the different brands that they were being fed. All right, so this is saying that the effect for brand is fairly large. Now, for eta squared, we don't have the same kind of cutoffs we do with Cohen's d, where the, like 0.2 was small, 0.5 was medium, 0.8 was large. But because this is a percentage, you know, we're used to seeing in psychology and stuff effect sizes that are, you know, 0.1, like 10%, 15%, 20%. That 20%, we're like, oh my God, this thing that we're doing, whatever it is explaining 20% of people's behaviors. That's actually a pretty substantial amount. So we're getting into levels of 42% and 52%. I mean, these are sort of massive effect sizes that you often, you know, won't see in real data, because this data was sort of made up about babies eating strained peas. It tends, you know, looks a little bit stronger than you might expect, but you know, these are evidence of like a really large effect for the brands and how it impacts sort of babies' eating habits of strained peas. Okay. Other measures. So like I mentioned before, we can use the same kinds of measures we talked about with t-tests. You can use Cohen's d. It usually makes sense to talk about the two groups, to only talk about two groups at a time, or effect size between the largest and smallest groups. That's usually the way it's done. You take the group with the biggest mean, the group with the smallest mean, and it'll give you like what the maximum Cohen's d would look like. And there, even if you can actually look up, do a Google search or something of converting eta squared values over to Cohen's d values to be able to get some metric of the 0.2, 0.5, 0.8. There, you can do that if you like, and you can do the other way around too. You can look up a Cohen's d value and convert that to an eta squared, and vice versa. So you still can do it. You're likely going to be, if you're going to be using these two, any of the two groups, either the ones with the biggest difference or whatever, you're likely going to take that pooled, that MSWG, the mean square for within groups, or within groups variance, or pooled variance, and you're going to take the square root of that number to give you a pooled standard deviation that you can use in your Cohen's d estimate. That's the way you want to go. And that's it for the one-way between groups ANOVA. So that's an extension of our independent samples t-test, and we're going to expand this idea in a couple different ways. One is we're going to take it into even more groups, but in a different way, in terms of adding more independent variables. So this is a one-way analysis of variance. So we're going to go into, well, what happens if we have more ways, where each way is referring to an independent variable. So in this case, our independent variable was brand of food, brand of baby food. But what if we want to add more independent variables in there? We can talk about doing something called a factorial ANOVA, which will be coming up shortly. And then the other option is, what if I wanted to expand the dependent samples t-test out to more than just two groups, or more than one repeated measure, right? So instead of just pre-post, why not do a pre-post and then maybe a 6-month follow-up or something as part of a study, or more follow-ups. Maybe you're talking about having someone come in and do a test over and over. Look at the STAR testing or SBAC testing now within high schools, K through 12 schools. You may be taking this same or similar math test from 7th, 8th, 9th, 10th, 11th grade, and be able to track those and be able to compare people across. So you can use something like a repeated measures ANOVA, which is the extension of the dependent samples t-test we did before. So those are coming attractions.